We are moving into the third speech. It is now my privilege to introduce our esteemed speaker of this session, Dr. Aiswarya Bhaskar, a luminary in the field of electrochemical energy storage. Dr. Aiswarya completed her PhD in 2010 at Technical University Darmstadt, Germany, in the field of high voltage positive electrode materials for lithium-ion batteries. She then enhanced her expertise as a postdoctoral researcher at Munster Electrochemical Energies Technology, Germany, until 2012. From 2013 to 17, she served as the group leader for the material synthesis for electrochemical energy storage at Karlsruhe Institute of Technology, Germany, while also holding a research scientist position at Helmholtz Institute, Germany. Her leadership in developing materials for energy storage application is widely recognized. Since 2017, as a senior scientist at Central Electrochemical Research Institute, Karaikudi, Dr. Bhaskar and her team have been advancing research in ion intercalation batteries, metal-air batteries, hybrid energy storage systems, and elucidating their mechanism. So we are truly honored to have her with us today. Let us warmly welcome Dr. Aiswarya Bhaskar to deliver her talk. Ma'am, please.
Yeah, so thank you, sir, for your very kind introduction. And I would like to thank the organizers for inviting me here, especially Professor Pradeep. He was my mentor during my master thesis time. So, as you know, I'm Aiswarya Bhaskar. I work as a senior scientist at CSIR lab, SICRI. SICRI is it's an institute dedicated solely for electrochemistry. It's Central Electrochemical Research Institute. So most of the scientists who work there, around 150 scientists, they are dedicated electrochemists. But I'm not a dedicated electrochemist. I'm more a material scientist than an electrochemist. And I know maybe mine is the first talk here on energy. I think so, because I missed to attend the morning sessions. And I will be talking about a very specific problem, which is on tuning the upper cutoff voltage for enabling cobalt 3+, 2+ redox in a P2, P3 spinel composite cathode material for sodium-ion batteries and in operando study. It looks a little complicated from the title, but it is very easy. And I will go from the basics because I think many of you here are not aware about batteries. Before I go to the technical part, I will just like to show you the activities which I am undertaking at SICRI. So my group is mainly focusing on different research activities. One is on electrically rechargeable zinc air batteries. That's a DST project, and currently we have a CSIR project, which is more in a device fabrication project, not like a fundamental research area. Then we work on lithium-ion batteries, especially cobalt-free and cobalt-less lithium-ion batteries. Everybody has heard of lithium-ion batteries, I guess, right? So it's nothing difficult for you. And then we work on sodium-ion and sodium hybrid batteries. Again, it's more an exploratory or fundamental research. And again, degradation and operating mechanism of lithium-ion batteries. So these are the major topics or project I am handling. And my group consists of PhD students, master students, and BTech students. We have a unique BTech program in Asia. It's one of its kind program. It's on BTech chemical engineering and electrochemical engineering. So we are like one of the CSIR labs out of very few which has a BTech program. Coming to my topic, so you don't need an introduction why we have to move from fossil fuels to more like greener energy sources. And the same reason we started working on lithium-ion batteries. I mean, not we, but the whole world started on working on lithium-ion batteries. And lithium-ion batteries are actually very attractive from a point of view of energy density, power density. That means if you use an EV, which has a lithium-ion battery pack, you can drive for long distance and you can drive at a higher speed if you use another battery system in comparison with if you use another battery system. But the major problems lithium-ion batteries are facing right now are the low natural abundance of lithium, high cost of lithium, and we don't have lithium resources in India. I mean, even though they claim that Kashmir has some lithium resources, it's not really like that we are mining any lithium in India. So most of the lithium are available in countries which are like politically not favorable for us, and there is a monopoly of some countries over the lithium mines. And that's why lithium also has a supply, volatile supply chain. So it has high cost, and again it has safety concerns, and it's environmentally incompatible, especially because of the lithium resources, where they are located and how they are mining and etc. And that is why we had to move to alternate energy systems. And one of the most attractive energy system in terms of lithium-ion batteries, in alternate energy systems, is sodium-ion battery. Before I go to the sodium-ion battery, I'll just explain how lithium-ion batteries work. So lithium-ion batteries consist of a lithium containing positive electrode or a cathode, and a lithium lacking negative electrode or an anode. And when we charge our battery, the lithium from the positive electrodes migrate through a lithium containing electrolyte and gets intercalated in the negative electrode, in between the layers of the negative electrode here, which is graphite, and the positive electrode is generally a metal oxide. Then when you discharge the battery, the lithium ions are migrating back and getting intercalated into the positive electrode. So now you heard a word, intercalation. Intercalation is nothing but the lithium ions or any ions will migrate from one electrode or get into another electrode without disrupting its original crystal structure. So why I am talking about lithium-ion batteries here? Because sodium-ion battery or magnesium-ion battery have the same electrochemical mechanism like a lithium-ion battery. They also use intercalation electrodes mainly. And there are other types of electrodes. I'm not going into the details of these electrodes. Then, coming to the major concern of a lithium-ion battery is safety. I think most of you have heard explosion stories from newspapers, right? The electric scooter was put to charge, and I think one whole family, they got expired in a fire accident. Or like Samsung Galaxy Notes were catching fire in the flight, and they were banned in the flights for a while in 2016 or 17, I guess. And so a lithium-ion battery, once you charge it, can actually store the same energy of a stick dynamite of the same size. And these are some of the examples of these safety issues, like Dell laptops were catching fire, and mainly because of the structural instability of one of the material which was using in this lithium-ion battery. So it's not like you put something, you take a cathode and anode, you just couple it and then you get a battery. But the crystal structure or solid state chemistry is very important when it comes to designing of battery electrode materials. And this was another incident where the Boeing 787 Dreamliner was catching, smoke was coming out of its wings, and then they figured out the reason behind was actually the thermal runaway of a lithium-ion battery. Thermal runaway is nothing but the lithium-ion battery, when it gets no parasitic reactions inside, will release heat, and which will further lead to explosion. So the reason behind this explosion is mainly oxygen evolution. And this oxygen evolution is mainly happening when you have an unstable positive electrode, or you have a negative electrode which is graphite, on which your lithium will go and plate, and this plated lithium is highly inflammable. It will catch fire very easily. So that's why lithium-ion battery, due to its high cost and the safety concerns, people were thinking of an alternative. And the most attractive alternative was sodium, especially in a country like India, because in India we have more sodium resources. Sodium can also be got from seawater. So we have a lot of sodium resources, and we have a good natural abundance. The working principle is very similar to that of lithium-ion batteries. And aluminum, normal lithium-ion batteries use aluminum as a current collector on the cathode side, and copper as a current collector on the anode side. Copper is very expensive generally. So if you can replace copper with any other metal, so in lithium-ion batteries, why we use copper is because the voltage of the negative electrodes working are not compatible with aluminum, and the lithium will form alloys with aluminum. But in a sodium-ion battery, we don't have a sodium-aluminum alloy formation. So we can use aluminum on both sides, cathode side and anode side. That makes it more cost-effective. Then for the sodium layered materials, we can find a variety of transition metals which can actually take part in electrochemical reactions. So when you come to the sodium ion materials, the positive electrodes have a huge classification, but the negative electrodes are very restricted, and the one common negative electrode which is used in sodium ion battery is hard carbon. I'm talking about the positive materials in our little lecture. So the positive electrodes are mainly classified into layered transition metal oxides, Prussian blue analogues, polyanionic compounds, and organic compounds. So what are the bottlenecks sodium ion batteries are mainly facing currently? I said we have restricted choice of anode materials, and even for the cathode materials, they are facing with low operating voltages, low stability of the solid electrolyte interface. What's a solid electrolyte interface? So normally in a lithium ion battery or any sodium ion battery, your electrolyte has a tendency to undergo flammable parasitic reactions when the voltage increases a certain limit. And if you have a very good electrolyte, or you have a component in the electrolyte, maybe an electrolyte additive, even without an electrolyte additive, some electrolytes will form initially a layer on top of the electrode surface by reacting with the electrode surface. It's called a solid electrolyte interface. An ideal solid electrolyte interface should be very uniform. It should be permeable to lithium transportation, and it should be stable. It shouldn't crack while you charge and discharge your electrodes. So lower stability of SCI is one of the problems that the sodium ion batteries are suffering from. And one major challenge that the R&D works or the research groups are facing is the sensitivity to humidity. So if you make a sodium ion battery electrode and a lithium ion battery electrode, the lithium ion battery electrode you can keep for several years outside. But if you make a sodium ion battery electrode material, if you keep it for a couple of months in a normal atmosphere, I mean, we know we are all living in a humid atmosphere, right? Look outside. So it has a tendency that it will go and react with the humidity from the atmosphere, and it will totally change the crystal structure. And crystal structure is very important when it comes to lithium intercalation. And lithium intercalation is the fundamental behind the battery. And that's why these materials should be stored in glove box or like in a dry room where the humidity is highly controlled. Another issue it faces is like limited reversible capacity. So the first generation sodium ion positive electron material was polyanionic compounds. The polyanionic compound sodium vanadium phosphate, it has a very low capacity, about 117 milliampere hours per gram. 117 is not enough when we compare it with a lithium ion battery. If you have a sodium ion battery and lithium ion battery, and if you want to have the same energy density, for a lithium ion battery, you can have the size of a very small pack like this. For the sodium ion battery, it will take a huge size like a load carrier. You know, in the old cycles, in the movies, we see these load carriers. It occupies such a space. So the energy density is very low for sodium ion battery when the capacity is very low. So the second generation of positive electron materials, that is Prussian blue analogues, they suffer from a difficulty in synthesis. we cannot synthesize Prussian blue analogues in a large quantity because the phase control is very difficult to modulate on. So we served polyanionic compounds and Prussian blue analogues, and organic compounds are there just like miscellaneous because they have huge issues, they suffer from the high voltage stability. That is where the layered transition metal oxides is highly attractive because the layered transition metal oxides have a higher operating potential and they have a high capacity and they are easy to synthesize, and you can synthesize it in a large scale. It's an upscalable synthesis route. So in our work, we focus on layered transition metal oxides, and these layered transition metal oxides are classified into different types again, like O3 type, P3 type, and O2 and P2 based on how the sodium ions are, where the sodium ions are occupying and how the layers are stacked. So O3 means the sodium ion is occupying in an octahedral site, and P3 means the sodium ion is occupying a prismatic site. And the 3 or 2 stands for the number of stacking layers that are repeating. So the O3 type and P3 type and O2 and P2, there are so many different types, and now the question is which one to choose. Overall, the layered materials have a high capacity and high ionic conductivity, and I said it's easy to synthesize. And now we can go through the advantages and disadvantages of these different types. So O2 is not a common type of layered materials which is favored in sodium ion battery, so it is very difficult to synthesize as well. So I excluded it. And in the P3 type, P2 type, which is a very common layered material, it has a limited diffusion barrier, so a faster kinetics. What does it mean? The sodium ions can migrate pretty fast in the system, and as a result, we can charge and discharge our battery at a high speed. So when you can charge and discharge your battery at a high speed, that translates to a high power density of a battery. So a material has a good rate capability, or the material has a faster kinetics, it means that you get a lithium-ion battery which is of a very good power density. And a P3 type material, they are also very good in similar to P2 type, but they suffer from irreversible phase transformations. I said crystal structure is very important. So if it undergoes a crystal structure transformation which is not reversible, then it will suffer from a permanent capacity loss in the system. That means your capacity initially, capacity means the amount of charge the material can store per unit mass. So the specific capacity will lose and the material will decay slowly. And these P2 type materials have lower sodium content, but P3 type materials have poor capacity retention. The O3 type materials are much attractive in terms of sodium content. And what is the relevance of sodium content? The more the sodium, the more charge it can store, the more capacity. So it can store more capacity, but the problem is, the major problem is it undergoes complex crystal structure transformation, or simple words, phase transformation, which are not reversible. So we omitted the O3 type and we are focusing on P2 and P3 type in our work. So the idea is that if you have a single material, you have also limitations. But if you can combine them in a molecular level, then we can end up in multi-phase materials. These multi-phase materials have synergistic effect from both the materials, and maybe it will act in such a way that your issues are overcome in the multi-phase materials. So we designed a P2, P3 composite materials expecting a high capacity and a good upscalability, and we can incorporate a higher sodium content than P3, so we will end up in a higher capacity material. We have investigated this P2 and P3 separately. I'm not going to show it here. And the P2, P3 composite also we have investigated, and we figured out the P2, P3 composite is behaving better. But in this special work, we are also going to incorporate a smaller spinel component in the crystal structure. The spinel components actually are not subjected to sodium ion intercalation or extraction because they are thermodynamically not favoring sodium ion intercalation. But the advantage is that by adding a spinel domain to the P2, P3 domains, we can impart higher electronic conductivity to our overall material. That was the major idea. Higher electronic conductivity will increase the rate capability, that is the lithium transport will be accelerated and we can end up in a higher power density in our battery. So this is the composition of the material we have synthesized. And we have also investigated literature. There are only 4 P2, P3 spinel structures reported in the literature, but nobody has bothered to understand why it improves the there is a suggestion that electronic conductivity is improving it, but what happens to the spinel phase during cycling? What happens to the layered phases during cycling? Is it completely reversible, irreversible? There were so many open questions, and these are the questions we try to address in this particular work. So we synthesized our material, and the material has about 51% P3 component and 36% P2 and about 11% spinel component we analyzed from the rate field refinement. And this material has actually a flake-like morphology. So you can see very nanometer sized nanometer thick layers in the material. And we have also investigated, we wanted to have not a composite material, but a structurally integrated material at the molecular level. That means in the same crystallite, we are expecting domains of the P2, P3 and the spinel, and we were very lucky, or we were happy that we got it like this. We could see in the same particle different domains, P2, P3 and spinel domains. So we could confirm from combined XRD and the TM analysis that we have a coexistence of these 3 domains, and we got a structurally integrated material. The next thing, we have analyzed it using ICP-OES just to fix the composition, and it was very close to the composition. So next was, the challenge was to understand the oxidation state distribution of the different cations in the material. So we have used X-ray absorption spectroscopy in collaboration with Petra. Petra is a synchrotron, DESI, Deutsche Elektronen Synchrotron, is a synchrotron source. I don't want to explain what is a synchrotron source, but it's an electron accelerator in simple words. It's located in Germany. So we have to write proposals, and when we write the proposals and it is accepted by DESI, we have a chance to perform our experiments there for those who are interested to know how we are doing these experiments. So why we didn't go for XPS, rather XAS, is because XPS is a surface technique. And most of the time what we have observed is that when we analyze our material with XPS, we see all divalent cations in the surface, but it doesn't mean we are seeing any electrochemical reactions from the divalent cations from the material. So that's why once you use X-ray absorption spectroscopy in transmission geometry, it's a bulk technique. We can get the oxidation state of your bulk. So the distribution of oxidation state in the bulk was found to be 4+ for manganese, 3+ for cobalt, and 2+ for nickel. And I want to say at this point, the 4+ manganese is not electrochemically active. Nickel 2+ is electrochemically active. Nickel 2+ can oxidize to nickel 3+. Cobalt 3+ is electrochemically active. The 3+ can always oxidize to 4+ if we give sufficient voltage. Now I talked about voltage, right? Now we are going close to the title, why voltage is important. So we did a cyclic voltammetry analysis to figure out the oxidation state, how the oxidation of the materials, the transition metal ions are happening inside the material. And we can see that the material initially, the black curve, initially after we assemble the battery, it was about 2.9 volt. And once you charge the battery, look at the black curve, it is cycle 1. We have an electrochemical reaction going around 3.5 volt. We mark it with 2 and 2 star, and we believe it is the activity of nickel and cobalt. And then we discharge the material to a voltage lower than the initial voltage. When we go below 2 volt, we are getting a new activity, a new electrochemical activity around 2 volt. And this new electrochemical activity could be associated with reduction of manganese 3 plus to manganese 4 plus. So the upper part, when it is a positive current, it is oxidation, and when it is a negative current, it is a reduction. And then when we charge the battery again, the 1 star, that is the manganese electrochemical activity, could be reversible. And then we are again getting the 2 star electrochemical activity correspond to nickel and cobalt oxidation. And how can we make sure that it is cobalt or it is nickel? So in principle, we can calculate a little bit, but if you want to see it by your own eyes, you can use operando techniques. Then when we subject our material, so it's a new material, so we subjected it to galvanostatic charge discharge studies. Galvanostatic means current is constant. So we keep the current constant and we apply a potential window, and in that potential window your battery is cycling. So when we did the galvanostatic charge discharge studies, we can see note that the voltage here is 4 volt. So we are playing around with a little bit with the voltage in this particular work, and we want to figure out how the voltage window is affecting your electrochemical mechanism. When the voltage is restricted to 4 volt, we can see the capacity initially is around 160 milliampere hours per gram, and after 50 cycles, it is retaining only 80% of the capacity, but that is normal for this material, and this behavior is much better than the normal P2, P3 or a P2, P3 composite. So we are actually improving the material by incorporating a spinel component, by getting a higher capacity and a better capacity retention. And this is called a voltage profile. In a voltage profile, we plot the specific capacity versus voltage. It can be correlated with the cyclic voltammetry you have seen before. So initially we see there is a plateau around 3.5 volt. This plateau is nothing but the reaction of nickel and cobalt. And the plateau around 2 to 2.5 volt is the reaction of our manganese. So in this particular material, we can see that initially the capacity is very low for the first cycle. It's only 60 or 40 because in the first charge, we are not activating the manganese couple. So from the first discharge onwards, we are getting also the electrochemical activity from the manganese, which adds up to our capacity. Then we performed rate capability studies in this particular voltage range, that is 4 volt. So rate capability studies are done by charging or discharging the battery at different currents, because then we can see that if your battery or your battery material has a potential to withstand different current rates. And this is the parameter which is translating to power density in a metal ion battery. Power density is, again I said, it determines the power of your battery. So this material has a much higher rate capability than its single parent compounds like P2, P3 or P2, P3. And this improvement in the rate capability was found because we have a faster diffusion induced by the spinel component with a high electronic conductivity. So we have a very good rate capability, especially at 5C, we got 86 milliampere hours per gram. Compared to half of that we obtained at C over 10. C over 10 means we are charging the battery in 10 hours and discharging the battery in 10 hours. 5C means we are charging the battery in about 6 minutes and discharging the battery in 6 minutes. So you see how fast we are charging. In 6 minutes we are getting approximately half of the capacity we got when we charged and discharged the battery in 10 hours. So this is a good observation, and then we can figure out we wanted to cycle the battery at higher current rate, that is at 1C and 5C. At both this 5C and 1C, we are getting a good capacity retention, and then initial discharge capacity about 92 milliampere hours per gram. So this material has a better cycling stability than its parent compound and a better rate capability than its parent compound. And now what we have done, we have increased the upper cutoff voltage from 4 volt to 4.5. And why we are doing it? We wanted to see if we can activate any other electrochemical reactions in the system. So what are the other electrochemical reactions possible? We already talked about nickel, cobalt and manganese, and we have already seen the electrochemical activity of nickel, manganese and cobalt. But we have one more anion here. We have an anion here, that is oxygen. And sometimes when you increase the upper cutoff voltage, you can actually activate the anionic activity, and the oxygen can undergo oxidation reduction reaction with a metal, like oxygen is oxidizing and the metal is reducing. It's called a decoupling. It's called a redox coupling mechanism. So we wanted to see if such a redox coupling mechanism occurs here. And we have increased the, how much more time I have? Okay, I'll finish in 5 minutes. Yeah. So we have increased the capacity, the operation voltage to 4.5. And at 4.5 volt, our capacity degradation was much higher, which is normal because your electrolyte will decompose at this particular voltage. And now to understand the reason behind it, we went to do in-operando methods. So why we do in-operando methods is like, if we are doing ex situ, that means we open the cell, we measure it separately, we can end up in loss of accuracy because the cell can undergo short circuit or like cell relaxation. And we have to do multiple cells in order to get any information from in-operando methods. And if we do multiple cells, we end up in multiple results. That is another problem. That is why we wanted to do while the cell is operating. And there are two different techniques. One is X-ray diffraction technique and one is an X-ray absorption technique we can do in-operando. So we did the synchrotron diffraction instead of X-ray diffraction because it is giving a more accuracy and a higher resolution. For the X-ray diffraction, the sample should be crystalline, and for an X-ray absorption, the sample can be amorphous. In X-ray diffraction, we can actually get no element-specific information, but with X-ray absorption, we can get element-specific information, all during operation. When you do the X-ray absorption spectroscopy, we have actually an edge position which gives you the oxidation state, and then we have a line shape that determines the local structure. So here we can see the oxidation state is different, and we have a different position for the lines. And here the oxidation state is same, but the crystal structure is different, or the coordination environment is different. We end up in different line shapes. And we are doing it in a setup like this. We made an X-ray transparent cell, and we are putting it to a cell holder and during rotation. And while the cell is connected to the electrochemical workstation, we are measuring the X-rays. We are passing the X-rays and we are measuring the absorption or diffraction. Then we charge and discharge our cell, and we can see that the manganese edge during charging in the 4 volt region oxidizes to manganese 4 plus during the discharge, and some residual manganese is also oxidizing during the charge. And during the second charging, the process is continuing. Nothing more than we expected in the 4 volt region. And the cobalt is also oxidizing from 3 plus to 4 plus. The initial oxidation state is 3 plus. And during discharging, cobalt is reducing to 3 plus. But below certain voltage, the cobalt is reducing to 2 plus. This is not what we were expecting. And again, from the next charge onwards, cobalt 2 plus 4 plus reaction couple is continuing. For the nickel KH, we are also seeing nickel 2 plus, nickel 3 plus oxidation reduction reactions. It's again what we have expected. And when we increase the voltage range to 4.5 volt, the manganese, interestingly, is not very active. So during charging, we are seeing a minor shift than the higher increased shift what we have seen during the operation voltage of 4 volt. But in the case of cobalt, we don't see any 2 plus. We see only the cobalt 4 plus to 3 plus electrochemical reaction. So just by increasing the upper cutoff voltage, we are actually, just by decreasing the upper cutoff voltage, we are actually tuning the cobalt 2 plus reaction. Then for the nickel 2 plus 4 plus, this is the major electrochemically active couple in this particular voltage range, that is 4.5. So we see 4 volt, we have manganese, nickel and cobalt 2 plus. And in 4.5, manganese is rare and cobalt is very minor and nickel is the only electrochemically active ion. Then when we did the X-ray diffraction or the synchrotron diffraction study, what we could see, for the 4 volt, when we restrict it to 4 volt, we can actually have a P2, P3 spinel to P3 to O3, and then a P2, P3 spinel is formed again, and it converts to a P prime to O prime 3 spinel. What does it mean? It means we have a 4-step phase transition. But as soon as we increase the upper cutoff voltage to 4.5, we are only seeing a P3 to O3, and then it is reversible and it is coming back to P2, P3 spinel. Is it better or not? The question here is difficult to say. Because even if we have a one less phase transition at this particular point, when we charge our battery, we are end up in a higher capacity loss. Probably here there is an activation of the oxygen anion. If you look at this figure, we can see that here, apart from the 2 star which was happening here, we see one of the electrochemical reaction occurring here, which is not corresponding to any transition metal element, and we can assign it to oxygen redox. And this oxygen redox can be confirmed probably by a metal reduction, and we have observed only a slight reduction of the cobalt 4 plus in the system. So in summary, what we can see is that, so I have only one summary slide left. When we have the cutoff voltage of 4, we have an electrochemical cycling is very good, and we have a high rate capability. And when we increase the upper cutoff voltage to 4.5, the electrochemical reactions are getting more in number, but we end up in a loss of capacity and less rate capability. And we can see that when the upper cutoff voltage is restricted to 4 volt, we can tune the cobalt 2 plus reaction. I'm going to the summary slide. We can tune the cobalt 2 plus reaction in the system. And with the N-operando methods, we can see that when the upper cutoff voltage is restricted to 4 volt, we have 4 phase transitions. But when it is restricted to, when it is increased to 4.5 volt, we have actually ending up in a reversible 1-step phase transition. The message here is there are 2 messages. One is that by incorporating a spinel structure into the P2, P3 composite, we can improve the electrochemical activity of the material and the overall electrochemical performance of the material. And the second is that by tuning the upper cutoff voltages, we can also tune the electrochemical reactions in the material. So with this, I conclude. I would like to thank all my funding agencies and my collaborators and my students. Without them, I couldn't show this work. So these are the works from my second PhD student, Aiswarya. I don't have a photo because I don't have any group photo where all are staying together. So I don't want a political issue, so I removed the group photo. So thank you all for your kind attention, even if it is lunchtime. Thanks.
Now it is a time for discussion. I request all to ask some questions, please. Yeah, you can have 2 or 3 questions, sir.
Excellent presentation. So this process of phase transitions which are happening in your solid, particularly if it is of a reversible nature, so you are taking a compound, it shows reversible phase transition. That is basically useful, right?
Yeah.
And but in your first summary, you had more phase transitions, right?
You mean it is not reversible?
I just wanted to confirm.
No, it is reversible. Only thing we are showing up to the second charge. So at the end of second discharge, it is reversible.
So this reversibility is for how many cycles, essentially? You are able to maintain the integrity of the crystal structure.
See, normally, if it is not reversible, how we will figure out? We'll do CV or like DQ/dV for long term. And when I can analyze the DQ/dV, that is the differential capacity plot after 100 cycles, the electrochemical activity regions will remain the same. But I don't guarantee that a percentage of material is dead. This is very difficult to analyze. If it is a small amount and it is difficult to figure out from X-ray diffraction, we won't be able to see that.
For your composite, I understand you are monitoring this process. So you have the electrochemical activity,
Yeah.
but you still do not know what is the active material. I mean to say you have a composite still. So
Sorry,
I mean to
didn't-
say you're going 100 cycles.
Yeah.
Is there still the integrity of the material? Can you do a bulk powder diffraction to see whether?
Yeah, we do. We
So
do
that-
post-mortem analysis.
So those things you do,
Yeah,
and
we
it
do.
is refill fitted to make sure the integrity of the phase is maintained,
Yeah.
and all these are reversible in nature,
Yeah.
essentially. Okay, and
But again, it is only 100 cycles we do.
so this
we
is
can't
where
comment.
you need. I think you need more research, right, in
Yeah.
sodium-ion batteries to
Yeah.
be able to operate much longer.
Yeah, much longer and much higher
So
voltage.
where do you think we need a modification at the structural level so that you can go to at least 500,000 cycles? Ideally, that is what you would like to target, right? So where do you think can you now do a change?
I think it is mainly solid-state chemistry where we have to play with. Material engineering.
But don't you think the thermal stability and the structural integrity of the parent lattice also needs to be looked at? Because I could not see any study on that part.
Yeah, that is true. That is true.
Maybe we can think about it.
Yeah.
Thank you.
We do it for lithium ion because lithium ion is more thermally unstable. For sodium,
but
it
for
is
stable
comparatively.
also, for sodium it will be good because of the fact that you're cycling it.
Yeah.
And you're susceptible to other things like.
Thank you, ma'am. Thank you to everyone. Now, personally, I would like to express my deep felt of thanks to the organizing committee for giving me this chance. And on behalf of the EFCS conference organizing committee, we would like to express our deep sense of gratitude and respect to ma'am. So, with a token of love, ma'am, please.
We extend our gratitude to Dr. Mohammad Mustafa TN for chairing this session.